Hi there. After doing the dynamic stability analysis of the distinct real roots case, now we will do the dynamic stability analysis of the repeated real roots case of the second order differential equation. Recalling the repeated real roots case, this was the general solution of it. We remember that this was the set of possibility of the particular integral depending upon the values of a1 and a2, and this is the deviation part represented by yc, and this is the exact value of yc in this case. So in other words, this is yc, or this is the deviation from the equilibrium. So we should focus on this because we want to get rid of this part or mitigate it and let the time path approach the equilibrium for the dynamic stability. Now we can compose this into its parts. We can see that this is the first arbitrary constant, and this is the exponential function where r is the root and t is the independent variable. The other part of the complementary function is appearing with the arbitrary constant and the exponential function. However, the independent variable is being multiplied, which is an additional term which was not there before. It will have a small role that we will understand as we go ahead. So we know that a3 and a4, they are the constants, and their values, they depend on the initial conditions. As we put t is equal to 0, we will get a3 and a4. And t is independent variable. Its range starts from 0 and goes to infinity. And we know that this is the equal real root case, and r is that root. Now do the hair splitting of this complementary function. It is quite synonymous to the distinct real root case because again we have an exponential function, and exponential decay will help us to reduce this term to 0. So this r, that is the equal real root, should be negative so that the exponential takes place, exponential decay. And here again the same sort of situation appears. However, this small t is getting multiplied this time. So how this can affect the overall result? It's basically a term that is being multiplied, and we will do the analysis of it in the following expression. In these lines, the same things they are written, and we are told that it doesn't reverse the dynamics of the exponential term because it is time and it starts from 0 and goes to infinity. So it's not going to change the sign of the expression, that is the exponential expression. It will keep the sign or retain the sign. So it's a multiplier, but it's neutral at the same time. We can start its value from 0 and we can take it up to infinity. So it's not going to change the nature of the result or change the sign, algebraically speaking. Now if we consider this part, it is basically the neutral multiplier, and this is the multiplicand, that is the term that is being multiplied with this multiplier. And whatever the result of this expression, this neutral multiplier, it is not going to change it. It is just going to affect it a little bit. For example, t will increase as we go ahead in time of the analysis of this expression. So exponential decay, it will be in process, and definitely it is due to this negative sign. So this t can mitigate this process of exponential decay, but it's not going to reverse it. So in this case, the exponential decay can slow down a little bit because of this neutral positive multiplier. So we are assured that both of these terms are going to give rise to exponential decay at their individual level. So on the whole, this overall term, which is the deviation, will fall prey to exponential decay, and as the time goes ahead, the deviation will reach to 0. Now we can verify this with the help of this numerical. You can see that we have taken two of the possibilities. Here the root is 3, so it's equal and appears on the other term as well. This is that neutral multiplier, and here the root is -3, so it appears on both sides. And t is there, that is the neutral multiplier. This 3 is the particular integral. So we focus on the deviation part, that is yc. It has two parts, the first part and the second part. This is the first part, and the root is positive, and again the root is the same, positive. It means that there will be exponential growth, and you can see as the time is going ahead, the exponential growth is increasing and increasing. So this is how it is happening here. And definitely when we sum these two parts of the yc, that is the deviation, it will also be increasing value, and you can see the result is there is substantial increase in the value. Now we come to the other possibility where the root is considered to be negative, and here you see that this negative sign is allowing us to have an exponential decay in both of these parts of the yc. So here we put the value, that is -3, and we solve it. And when we do, with the help of these various values of t, that is 0 till 5, you can see the value is declining further and further. Here again we can see that the decline is there. As you can see that this term is getting close to 0 as we go ahead in time. But this 0 is a little confusing because 0 is less than 0.04 and all other of these values. This 0 is there because this neutral multiplier is 0 in this case, as the value of t, that is the neutral multiplier, is 0. So whatever the result of this term is, that is the exponential term, it will reduce to 0 because of this t is equal to 0. This is why this first term, which could have been non-zero and greater than this term, is still 0, because this neutral multiplier reduces this exponential term to 0. However, the remaining terms, they are showing a consistent decrease, and hence we can say that both of the parts, they have exponential decay. So when we sum these parts of the yc, they are showing a declining trend, and clearly the conclusion is that in the first possibility, when we observed the components, they were increasing, so deviation was also increasing, and in this case the exponential decay was happening, so deviation decreased. Convergence is imminent, and the equilibrium is considered to be dynamically stable. Here there was divergence as the deviation was on the rise, and the dynamic instability is the consequence of it. So the conclusion, the formula or hack or signal of having a dynamically stable equilibrium in case of the equal or repeated real roots, is that the root should be negative. So this is the formula or identification of a dynamically stable equilibrium in case of the repeated real roots case. You can see this is the numerical testimony, and this is the decomposition of the deviation part, and that expression is explained. This was the overall solution, and this is what we wanted to do, that is the analysis of the dynamic stability of the repeated real roots case. And in the next video we will do the dynamic stability of the complex roots case.